presentation of the day, and that is how nanoparticles, something so insignificant and small of these small particles and molecules, can help us to potentially be the forefront of the next generation of our cancer research. As many of you may know, cancer is one of the prime examples of a disease that we humans have struggled with since the beginning of humanity. But cancer is very unique in the fact that, unlike most other diseases where you're having other pathogens come into your body and infect you, cancer is an example of when your body infects itself. Well, how does it do that? Does anyone know how cancer works and would like to tell us? Yes, Alec.
The gene that regulates cell proliferation and what's it called? There's a transfer for cell death that goes wrong.
Right. So basically, these damaged or mutated cells can't control when and how they divide. So when they divide, they do so uncontrollably, and that forms a mass called a tumor, which may spread to other parts of the body. So this is a very large problem that we are facing. As I've stated before, cancer is one of the most pressing issues in this aspect of medicine, and lots of our treatments currently focus around using chemotherapy or radiation therapy. As you might notice, some of these treatments, sure, they might be effective for some people, but they are not universally effective, nor do they avoid the many side effects that come along with these treatments. And before I'd like to dive deeper into this explanation, I want to introduce, well, what is the field of biochemistry? As Professor Lander of MIT states, we biochemists are interesting creatures. When we see a butterfly fluttering around in the cold winter air, our first thought is to homogenize this butterfly. In other words, we grab this butterfly and we stick it in a blender. Then we find how this butterfly is able to fly from that homogenized that homogenized mixture of butterfly puree. Okay. From that butterfly puree, we are able to isolate individual compounds, molecules, and proteins that may be able to help us to find, well, what is the central dogma of how this butterfly can fly. And much the same principle applies to nanoparticle cancer therapy, when we're looking at the smaller aspects of life and chemistry to answer larger questions. Raise your hands if you know of or are acquainted with anyone who is currently struggling with cancer or has struggled with cancer before. So yeah, good. I see lots of your hands up. Cancer is one of the most common causes of death in our world, accounting for about 1 out of every 6 human deaths per year on the Earth. Some of the treatments that we currently have are effective to their own merits, but they aren't simply effective enough. So let's take a look at those. In the past, we've used a variety of different treatments, such as chemotherapy as well as radiation therapy. However, when you associate chemotherapy with lots of the side effects, you truly see the connections between these two aspects of medicine. And that is, well, when you think of cancer, you think of, well, people who have cancer, their hair falling out, or an excessive amount of vomiting. All of that is caused by the chemicals and the damages that it causes to your own body. As you all may know, cancer cells divide rapidly, but so do your hair cells and your stomach lining cells. When cancer cells are being killed, so are some of your healthy body cells. So, not the best treatments that we currently have. We also have, in the form of immunotherapy, a new emerging idea, and that is to use oncolytic viruses, or cancer-attacking viruses, to solve the problem. Here we have our friend, the T2 bacteriophage. Kind of looks like a spider. Now, the T2 bacteriophage, its natural enemy is Escherichia coli, and it will seek out these bacteria to attack and infect, just as other viruses would do. Except with T2 bacteriophages, we are finding that we can genetically modify them to attack just cancer cells. What is the merit behind that? Well, we're able to help the immune system recognize that these cancer cells must be eradicated, as well as killing cancer cells in the process with viruses. However, this treatment has its reservations because, after all, we're injecting viruses, other things that might also make us sick, into our bodies, and that is some cause for concern. When it comes to nanoparticle therapy, we need to cast aside one of our modern beliefs, and that is the modern belief that bigger is better. A big house, a big car, a big swimming pool. It seems quite inconceivable that something smaller would be for the better. However, when it comes to nanoparticle therapy, that is exactly the case. We need to quit looking at the macro solutions and instead turn to nano solutions, and that is seen within the research currently being conducted at MIT. The aim for nanoparticle therapy is to develop a type of bottle brush drug that's modeled after a class of chemical compounds called IMDs, or imidazoquinolines. Imidazoquinolines, they help to stimulate immune response by the release of inflammatory cytokines. And the goal is to be able to have these drugs both kill cancer cells due to the nature of these anti-cancer drugs, as well as activate immune response toward these cancer cells. And the way they do that is through activating toll-like receptors on the surface of your immune cells. So, moving on to some visualizations of this topic. Here we see, on the far left, a toll-like receptor. On the surfaces of your cells, there varies in number, but there's usually around tens or even hundreds of different protein receptors. On immune cells specifically, toll-like receptors are very prominent because they play a part in stimulating immune signaling cascades. Now in the center, you'll see some of the various implications behind nanoparticles in cancer therapy, other than the fact that, well, we can use them to engineer new cancer drugs. And finally, on the right here, that is an example of an IMD, bottle brush drug. As you can see, the shape is fairly reminiscent of that of a bottle brush. That will combine a great number of cancer drugs together while also being able to stimulate the immune system. And we'll see how that works in the next slide. This is an example of a TLR signaling pathway. So as you can see, those are multiple toll-like receptors on the surfaces of immune cells, and ultimately that leads to the release of inflammatory cytokines. Now that we've set the solid foundations for this topic, it's time to investigate how these nanoparticle drugs actually work. They're modeled after imidazoquinolines, which are a class of chemical compounds. And what's special about these chemical compounds is that they have an R group on the side that's able to stimulate the toll-like receptors in starting the pathway. However, IMDs themselves, these chemical compounds that are somewhat naturally occurring, they themselves are a little too good at their jobs. And that means overinflammation, which in many cases of overinflammation causes more damage to the body than cancer cells ever could. And to illustrate that, I need all of you, no matter how effective these IMDs might be, to curb your enthusiasm. Okay, enough of how do you Hello? Okay. Okay. Enough enough of William Chang making him a fool of himself in public. Let's get back to the task, and that is to state that bottle brush drugs, these bottle brush drugs, they will serve the same purpose as these IMDs themselves, but they will be more regulated to cause not as much inflammation within your body. And that is the key behind how nanoparticle drugs work. To follow up with this response, I'd like to also emphasize that IMD bottle brush drugs and the field of biochemistry are ever evolving. There's more information to be found, and there always has been more information to be found about this subject. This information that I've just presented was actually discovered in just May of this year. And just 2 months ago, well 3 now, in September of this year, researchers were finding new ways for nanoparticles to contribute to cancer therapy. For example, there is immense hope and belief that we could engineer some nanoparticles to serve almost as cancer lysis vaccines, which will both protect against cancer cells and their antigens, as well as killing these cancer cells outright. So what are some of the results of this research? Well, first of all, we see that these nanoparticle bottle brush IMD drugs, they're being able to minimize the side effects of such treatments, so that these people won't have to suffer from, say, excessive vomiting or hair loss. But also, this research is currently undergoing clinical trials. At least in mice, what's been found is that cancer cells within the mice are completely being eradicated, with the mice suffering little to no side effects at all. And this fills us up with a lot of different hopes for this new generation of cancer therapy. Some of you indicated that you know other people who are struggling with cancer. So truly, we'll be able to find whether or not nanoparticle cancer therapy can be the forefront of our cancer treatment in generations to come. And just to illustrate how important this is to our modern understanding of how chemistry is always contributing to our medicine and our medical field, I'd like to leave you a quote from myself, and that is nanoparticle.
Oh my god.
Nanoparticle therapy. Split in the big stuff and look at the smaller scale to find the solutions. Thank you.
Where was that MLA formatting on the citations, bro? Come on.
Why do you have 3 phones recording you?
I don't know. Everyone wants the blackmail of the dancing.
Fucking greedy.